Alrighty, welcome to the Electronics 1 review for fall 2017. We'll be going over a few questions from past quizzes and exams. So our first question is this problem right here. So we have a simple circuit with a voltage source, resistor, and then a diode. So the first thing, and what we're asked to calculate is we're going to be drawing the DC load line, using a graphical method, finding the approximate values for IQ and VQ, and then also calculating RD, and then repeating these same steps for a different voltage source value. So to start this off, we'll redraw the circuit. VSS here, our diode, and then our givens, ID plus minus VD. So, and then this value of R. So R is given to be 200 ohms, and initially VSS is given to be 4 volts. So to start this problem off, we're going to be calculating ID. So ID, or the current through the circuit, is going to be VSS over R. So that's going to be 4 volts over 200 ohms. This is going to be 0.02 amps or 20 milliamps. So our curve is going to look something like this, right? Just a standard curve for a diode, where this is ID and VD. So we know that we're going to have at least one point up here at 20 milliamps. But if we want to draw the load line across this curve, we're going to need a point over here. So that point should be where VD is equal to VSS. So essentially we have where the VD is 0 and we have maximum current, and then where we have no current and maximum voltage, which is also equal to 4 volts. Now, as in with this question, you'll be given a graph that actually shows where you can draw your lines. But as you can see, this graph doesn't extend all the way down to 4 volts, so he started to write the equation for this line. Thank you. So what we can do is we can say, oh, rise over 1. We know we want 4 volts here and that we want a straight line, so we can just do these 2 points. 0, 20 milliamps, and 4 volts, 0 milliamps. And then labeling this x1, y1, x2, y2. If you do y2 minus y1 over x2 minus x1, you get 0 minus 20 over 4 minus 0, negative 5 milliamps per volt. And then using that slope, y equals mx plus b, negative 5 times VD plus 20. Now, since we can pick literally any point, but since we want to actually cross the load line, he picked just this point along the line. So if we pick VD equal to 2, we'll see that y is equal to 10. So negative 5 times 2 plus 20 is equal to 10. So that's why he was able to draw this line here. So once you draw that line, you can use a ruler and find out the values for IDQ and VDQ. So you're going to take the point where it crosses the line and then draw straight down. as well as straight across. So this value representing VDQ and this value representing IDQ. So looking at the graph, we can approximate the values as 14 milliamps, as 14 milliamps and 1.8 volts, which is where he's pulling these numbers here, since this is approximately 1.1, close to 1.2, 1.8. All right, so now that we have that, so we decided that VDQ for the first, so VSS is equal to 4 volts here, is 1.8 volts, and IDQ is equal to 14 milliamps. So the next thing we need is RDQ. Well, RDQ is equal to 1 over the slope of the tangent. The tangent being this line here. So if you take your ruler and just draw a tangent line to that quiescent point, you'll find that, oh, this now you have now you can calculate the slope of this tangent line by looking at the rise, which is the same as value as IDQ, and the run, which is going to be the difference between this VDQ value and where it crosses here. Where it crosses here. So this crossing is approximately 1 volt this way in width. So it's approximately at 0.9. So since we can just calculate the slope of that tangent line first. So the slope of the tangent is going to be equal to the rise, IDQ, over the run, which is going to be VDQ minus that 0.9. So that's going to get you 14 milliamps over 1.18 times 0.9, which gets you don't forget your units. .05. And so since RDQ is equal to 1 over 0.05, that gets you 20. So approximately 20 ohms should be the value of RDQ. So now we can repeat the same process and calculate the same constants, the same numbers for VSS equal to 1 volt. Again, we'll calculate the current first. So ID is equal to VSS over R, 1 volt over 200. Which is 0.005 amps, which is equal to 5 microamps, or 5 milliamps. All right, so now, again, looking at this line, or this relationship, you have 5 milliamps, which is down here, Again, you have 1 volt. So again, calculating that with this graph, you'll have an exact point values, so you don't necessarily have to calculate the equation for that line. So again, you can take a ruler and you draw this line. And then looking at this point, you could again approximate IDQ and VDQ. Which VDQ is going to be 0.6, 0.7, and IDQ is going to be approximately 1, 1.5, in between there too. Okay. Then now, since you have a VDQ of 0.7 volts and an IDQ of 1.5 milliamps, we're going to calculate RDQ again, which of course is 1 over the slope of the tangent. Looking at this point right here, draw a tangent line. And this line approximately goes through, well, here's 0.05, so it's right about there. So we're going to first just calculate the slope of the tangent. As equal to IDQ over VDQ minus 0.5. So that's going to be 1.5 milliamps over 0.2. That's equal to 0.0075. And so now RDQ is equal to 1 over 0.0075. All right, so the answer should be 133 ohms approximately. All right, and that is how you solve these two. This one should be 133, and this one should be approximately 20. Next, we're going to be doing an op-amp problem from the same quiz. And op-amp problems are really fun because they're really just an extended application of node voltage law. So how this problem is broken down is if you write out the equations, that's a couple points, as well as the correct answer is a couple points. So writing out your equations properly, even if you mess up on the algebra and don't get the question right, will really help you in improving your score. So I recommend that you write out all of your node voltage equations beforehand. All right. So I'm going to redraw the circuit here. Problem 2. Vn plus minus, and it's important to note that we have a positive 10 volt supply and a negative 10 volt supply. That's going to be important to determining whether our answer is correct later on. Here's R1 going to ground. This is also going to ground. We have R2, R1, R2. And here is RL. Alrighty. So first thing to note is that we're using the ideal op-amp model. So that means the input resistance is equal to infinity, and the output resistance is equal to 0. And then the open loop gain A is also infinity. So, first off, we're going to write out those node voltage equations. So looking here, we see that this is going to be the Vn, or the Vn positive, or Vp. And that's going to be equal to Vn. And since Vp is equal to Vn, this Vn here is also going to be equal to Vin. So right here we have Vin. So looking at this node first, since we have no current going this way, and all the current is going this way and this way, we're going to have Vin minus, and we're going to label this node V1, and then this node V out. So Vin minus V1 over R2 plus Vin over R1 is going to be equal to 0. So that's our first equation. Second equation is going to be V1 minus Vin over R2 plus V1 over R1 plus V1 minus V out over R2 is equal to 0. And then our third equation is going to be analyzing this node here, and we're going to have V out minus V1 over R2 plus V out over RL is going to be equal to 0. So those are the three equations, three unknowns. Those, well, actually two unknowns, since we have Vn given in the problem as 2 volts. R1 is equal to 2K ohms. R2 is equal to 1K ohm. And RL is equal to 4K ohms. So really all we don't know is V1 and V out. So let's solve this first equation for V1, since we have all of the other inputs. So solving equation 1, we have 2 volts minus V1 over R2, which is 1K, plus 2 volts over R1, which is 2K, equal to 0. So 2 divided by 1K. It's going to be 2 milliamps plus V1 over R1K plus 1 milliamp is equal to 0. So moving this to the other side and this to the other side, you have V1 is over 1K is equal to minus 2 milliamps minus 1 milliamp, negative here, milliamp. So you get minus 3 milliamps, and then multiply by negative 1K is equal to V1. That will get you 3 volts. And then using equation 2, we can solve for V out, in that we have 2. We have our newly found 3 volts minus 2 volts over R2, which is 1K, plus V1, which is 3 volts over R1, 2K, plus 3 volts minus V out over R2, which is 1K, is equal to 0. So here we have 1 volt over 1K, which is 1 milliamp. Here we have 3/2 milliamp. Plus, breaking up this fraction, we have 3 milliamps minus V out over 1K equal to 0. So moving these 3 values over to the other side, you have negative V out over 1K equal to negative of 1 plus 1.5 plus 3. So that's obviously 5.5 negative milliamps minus V out over 1K. And then solving for V out is equal to 5.5 volts. So that's the first part of this question, is find V out. And now that we've found V out, we also want to know the current coming out of this op amp. Now the current coming out of this op amp is going to be the current coming out of, or through this branch right here. So this current, I op amp, then there's this current here, IL, and then this current going back here we'll call I1. So looking at this node, I op amp is going to be the sum of IL plus I1. Well, IL is going to be, via Ohm's law, the voltage out over the resistance of the load, plus the voltage out minus V1 over R2. Voltage out is 5.5 volts. RL was given as 4K ohms, plus 5.5 volts minus 3 volts over R2, which is 1K. So I op amp is going to be 5.5 divided by 4 plus 2.5. Yeah. So it should be 3.875. Now, did I do that wrong? Milliamps? Let's see. 5.5 plus 3. Nope, 3.875 milliamps. Okay. Alrighty, and that is the end of the first quiz. Next thing we're going to cover is one of Alavi's old exams. I'll just go ahead and flip through it so that you guys can take a look at the questions before we start to work them. Alrighty. We're going to be working on problem 2, since problem 1 was something that we've already done. So we're going to be looking at calculating the majority and minority carrying concentrations in a p-n junction. So first we're given in the problem that the temperature that we are at is 300 Kelvin, that we have an accepted doping concentration of 10 to the 18th per centimeter cubed, and a donor concentration of 2 times 10 to the 17th per centimeter cubed, and that we have a cross-sectional area of 10 to the negative 4 centimeters squared. So to start off, to calculate the minority carrier concentration, we're going to be using this formula. P naught N P naught is equal to Ni squared. And since we know that N P naught is approximately equal to Na, we have that value. And Ni at this temperature is going to be 1.5 times 10 to the 10. So since we have Ni and NPO, we can calculate the minority carrier concentration, PP naught. Is equal to 1.5 times 10 to the 10 squared over 10 to the 18th, which is equal to 225 centimeters. We're going to do a similar step for the inside. So this was all of the P side, inside. So we're going to be using this formula. Again, Ni is going to equal 1.5 times 10 to the 10. N and naught is going to be approximately equal to Nd. So again, we're going to calculate the minority carrier concentration. P n naught is equal to 1.5 times 10 to the 10 squared over Nd, which was 2 times 10 to the 17th. It becomes 1.125 centimeters per centimeter cubed. Now, we're also asked to calculate the built-in potential in this p-n junction. So to do that, we're going to be using the formula V naught is equal to the thermal voltage natural log of Na Nd over Ni squared, where Vt is going to be approximately 26 millivolts. Na is again going to be, or Na is going to be the value we were given, which is 10 to the 18th. Nd is going to be 2 times 10 to the 7th. And Ni is going to equal 1.5 times 10 to the 10. So writing that out, we have V naught is equal to 26 millivolts, natural log of 10 to the 18th times 2 times 10 to the 17th over 1.5 times 10 to the 10th squared. And running that through the calculator, sure we have enough parentheses. Divided by 1.5 times 10 to the 10th, all of that squared. And taking a look at the result, make sure that that makes sense. So that gives us an approximate intrinsic voltage of 0.894 volts. Finally, we're asked to calculate the depletion width of the region. So, the depletion width equation is this. Square root 2 epsilon s over q, 1 over the acceptor concentration plus 1 over the donor concentration, times V out. So we're given that epsilon s is equal to 111.7 times epsilon naught, with epsilon naught being 8.854 times 10 to the negative 14th. Q is Coulomb's charge, 1.6 times 10 to the negative 19. And that V naught is the V naught we calculated earlier as 0.894 volts. So, plugging in all of those numbers, we have 2 times 11.7 times 8.854 times 10 to the negative 14th, all over 1.6 times 10 to the negative 19th, 1 over NA, where NA is 10 to the 18th, plus 1 over ND, which is 2 times 10 to the 17th, times 0.894. And at this point, it becomes plug and chug. Two times 11.7 times 8 times 10 to the negative 14th over 1.6 times 10 to the negative 19th, and then that is times 10 to the 18th to the negative 1 to make it a reciprocal, plus 2 times 10 to the 17th to the negative 1, and outside that times 0.894. And look at this to make sure, oh, the 10 to the negative 19th term didn't go where I wanted it to go. Times 10 to the negative 19. Let's see, make sure there aren't any other mistakes. Nope, looks good. So that results in, let's see if we can, 8.33 micrometers, which is the width of the depletion region. And that is the end of that problem. So here we have a BJT, and for this he's asking that we write out all of our equations as part of the breakdown of the points. So again, you're going to want to write all those equations out, make sure he can see them. And also note that he wants us to use VBE as a constant 0.74 volts. But other than that, we're just going to go along with the numbers he's given us, and beta, of course, is 100. Alrighty. So I'm going to redraw this BJT circuit in a way that sort of helps me look at it and write my equations. I'm going to make this 9-volt source connected to RB. Here's RC, 18 volts. Here's RE, and then here's my ground. Here's VB. So we're going to be doing 2 loop equations, and then also the equation that relates IC, IE, and IB. So going around this loop, right? Actually, I think, oh well, either way. So with this loop, we hit the negative 9-volt source, plus, and since IB is going to flow this way, we're going to have plus minus, so we're going to have plus RB, IB, plus VB, and then finally IE is coming down this way, so we have plus minus, so plus RE, IE equal to 0. And then going along this loop, we're going to have negative RE, IE, plus minus VCE, so minus VCE, plus minus, right? So plus RC, IC, and then plus your 18-volt source equal to 0. And then, of course, rearranging this around, you have RB, IB, plus VBE, plus RE, IE is equal to 9 volts, and 18-volt RE, IE, plus VCE, plus RC, IC is equal to 18 volts. But finally, we still have one more equation, which is the equation for this BJT, right? Is going to be IE is equal to IC plus IB. Sorry, this is supposed to be a lowercase I. So, to start off, we're also going to have another equation, right? Because IC is equal to this beta factor times IB. So, by plugging this equation into here, we can get that IE is equal to beta IB plus IB, which factoring out the IBs, you have beta plus 1 IB is equal to IE. Well, this relationship helps us a lot, because if we look at equation 1, we can take IE, plug it in, and solve this equation for IB. Let's go ahead and do that. So, working with equation 1, we can restate it as RB, IB, plus VBE, excuse me, plus RE, beta plus 1, IB is equal to 9 volts. So, since we're given VBE, we're given RE, we're given RB, and we're given beta, we can solve this equation for IB. So let's go ahead and do that. We have RB as 110 ohms, and then factoring out that IB, plus RE, which is 3K, times beta, which is 100, plus 1, is equal to 9 minus VBE, which is 0.74. And so then plugging this into the calculator, we have just leave that. So 9 minus 0.74 divided by 110 times 10 to the third plus 3 times 10 to the third times 100 plus 1. And that gets us a value of 2 times 10 to the negative 5 amps, which would be 20 microamps is IB. So now that we have IB, we can also solve for IC, because IC is equal to beta plus 1 IB. So 101 times 20 microamps is going to be 2.02 milliamps. And since IC is equal to beta IB, you can also do 100 times 20 microamps. What this number? So that's just going to be 2 milliamps. Cool. Alrighty, so now that we have those three values, we can figure out VCE. So VCE was part of equation 2, where we had 18 volts is equal to RC IC plus VCE plus RE IE. Well, for solving for this, we can do 18 minus RC IC minus RE IE is equal to VCE. So 18 minus RC being 5K times IC, which was 2 milliamps, minus RE, which is 3K, times 2.02 milliamps is equal to VCE. (18 minus 5 times 10 to the third times 2 times 10 to the negative third minus 3 times 10 to the 3 times 2.02 times 10 to the third. So that's going to equal 1.94 volts. And here we're going to check to make sure that we are in the region that we're thinking we are in. So assuming that this is in the forward active region, that means that VCE has got to be greater than 0.2 volts. And since 1.94 volts is greater than 0.2 volts, check we are in the active region. Alrighty. So, part C of this problem says, now suppose we completely remove RE. Well, if we completely remove RE, this is what our circuit's going to look like. We'll still have the 9 volts. Oh. The resistor. That resistor plus 18 volts. Here's RB, here's RC, plus, and don't forget VBE, and plus minus VCE. Cool. So again, going around these equations, this one is going to change a little bit. You have minus 9 volts plus IB RB plus VB is equal to 0. And then go around this way. You've got minus 18 volts plus RC IC plus VCE is equal to 0. And then, of course, you still have the relationship IC is equal to beta IB, and IE is equal to IC plus IB. Well, since we already have VBE, RB, and 9 volts, we can figure out what IB is. So IB is going to be 9 volts minus VBE over RB, which is going to be 9 minus 0.74 over RB, which is 110K. So we have 7.5 times 10 to the minus 5 amps, which is 75 microamps. And since we have that, we have the fact that IC is equal to beta IB, small I, 100 times 75 microamps is going to be 7.5 milliamps. So, and then finally, IE is equal to beta plus 1 IB. So that's going to be 101 times this value here. So slightly different, 7.58 milliamps. Okay. So we're going to look at now calculating what this VCE value is. So now that we have IC and IE, we can continue to analyze this problem. But one thing to take note is that we're dealing with a real source here. So if we look back at our network, we have this 18-volt source and this RC. So what's the maximum current that can flow through this circuit? Well, IC max is going to be 18 volts over RC, which is 18 over RC is 5K, I want to say. 5K, which is equal to a value of 3.6 milliamps. Well, if we have 18 volts, if we have a maximum of 3.6 milliamps, but we're trying to draw 7.5 milliamps, that means we've saturated this device and that we're not going to be able to draw out this much current. So if we saturated the device, that means that VCE has limited itself to 0.2 volts. So going back and looking at this second equation, we can actually figure out the real value of IC. The real value of IC is going to be IC is equal to 18 minus VCE over RC. 18 minus 0.2 volts over RC is going to be 18 minus 0.2 divided by RC, which is 5 times 10 to the third, which is going to be 3.56 milliamps, less than the value we calculated up here. And with IC in our hands, we can figure out IE and IB. So that's going to be IC over beta. So that's going to be this value divided by 100, which is going to be 36 microamps. And that should be 101 times 36 microamps. So it's approximately equal to 3.59 milliamps. And so now we have VCE, IE, IB, and IC for the case where RE is equal to 0. Alrighty, so that was the end of that problem. Now we've got 2 problems left, so then we have this problem here, which we're going to let you attempt on your own. It's very similar in that we're going to be doing simple equations to solve for VBE and VCE. And what you're going to do is you're going to calculate the fact that IC going around this loop is going to be equal to 10 milliamps as a function of VCE. So in VCE is going to vary between 0, where it would be 10 milliamps, and 10 volts, which is the limit on that VCC source. So then you can draw the load line, as well as draw the different regions where you are in your forward active or in your saturation region. But we'll let you guys handle that on your own. Finally, we're going to be working on this op-amp problem. So this op-amp problem is very similar to the one we did in the quiz, except for that we're going to be kind of working backwards. So we have this source plus V1 that is here. I'll let you take a look at the whole problem first. And then be redrawing this network. Okay. And the goal of this problem is to figure out the regions in which you are in the linear or where you've saturated this op-amp. Now, to saturate an op-amp, you've basically increased this voltage source to the point where you are now trying to have this output voltage higher than the values of the power supply. So the positive power supply, in this case, is 9 volts, and the negative power supply is 12 volts. And we're also given that R2 is equal to 2R1. Now we're given that this is also an ideal op-amp. So we have infinite loop gain, zero input resistance, or infinite input impedance, zero output resistance. So we can solve it using those equations. So since Vp is equal to Vn, and Vp is equal to V1, we can see that V1 is also at this node here. So V1 over R1 goes to ground, is the current coming out of here, and the current going this way is going to be V1 minus V out over R2, and that's going to be equal to 0. All right, so now solving this using the fact that R2 is 2R1, we can do V1. So let me just rewrite that. So V1 is equal to 1 over R1 plus 1 over 2R1 is equal to V out over 2R1. Adding these two fractions, you have 2 over 2, so you get 2 over 2R1 plus 1 over 2R1 is equal to V out over 2R1. So that's 3 over 2R1 V1 is equal to V out over 2R1. Then multiplying this and dividing by that, V1 is equal to V out over 3 V out over 3, since the R1s cancel. So now to draw this, we have to take a look at what values, or to find out where the op amp is going to saturate. We have to look at where V out can go. So V out is going to be between these two values. So it's going to be less than 9 volts, but greater than negative 12 volts. So that means V in, as a function of V out, if we plug in 9 volts, V1 or V in is going to be less than 3 volts, but greater than negative 4 volts. And in between those two values, it's going to be linear. So we can take a look at this graph that you're provided on your test. So we have the ceiling of 9 volts and the floor of negative 12 volts. We know that at V1 equal to 3 volts, we're going to get 9 volts, so that gives us this point here. We know that at negative 4 volts, we're going to get a value of negative 12, so that gives us this point here. And then you can take a straight edge and connect the two in a straight line. And since you know that you can't actually get more than 9 volts out of this, you're going to have a saturated level here. Oops. And since you can't get less than negative 12 volts, you're going to have another level here. And in between, it's going to be just a straight line linear. And so it's very similar to the one we did on the quiz. You're just working a little backwards using the same principles. And just finding V in, or the input, or V1, as a function of the output. And since you know the range on the output is going to be between 9 and negative 12, you know at what points you saturate. And that's how you solve that problem. This has been the review for Electronics 1 in the fall of 2017. Thank you.